Hello, everyone. Welcome back to the computer organization and programming class. So we're going to begin this week continuing on what we started it last week, which is stack. And we know why a stack is important. Looking at the facts last week, we learned that without a stack, we cannot build a method or a function. So it is very important to understand the stack in order to understand how a program works, because a method is nothing but a set of instructions. It's a program, right, guys? So last time we looked at the theory, we looked at how push and pop works, and we learned few facts. Let me see if I can use the annotation right here. So what we did last time, we looked at, let me just choose, okay, so we looked at how push and pop works, right? So we say push, and we know when we do push, we subtract from the stack pointer, right? We subtract 4, and when we pop, we actually are adding 4 to the stack pointer, right? So if this is your memory start from low to high, right? So the stack grows the other way around, it's from high to low. So if you want to move back toward, against the growth of the memory, you need to subtract, because you want to grow from 100 maybe to 96. Why 96? Because the stack pointer is a 4-byte register, right? So that is the stack pointer. So that is the ESP. So the stack pointer usually points where? Points at 4 bytes. So if you are 100 and you want to go down, you subtract 4. So you're going to go to the 96. You're going to go further down, you're going to subtract another 4, so you're going to get 92. So that is the top of the stack now. It points right here. Okay, so that was the theory last time, and we learned how the stack works. I'm trying today to share with you the idea of the application of this theory. So I just want to go back into this Visual Studio. Hopefully, it's going to be a great experience, and we're gonna look at that. Okay. So let me go right here. Let me go right here, if possible. Let me see. Okay, and let me start writing the code. So let's say if we're gonna say push 5, or let's say push 7, and then push 6, and then push 5. Okay, I'm sorry. Okay, so we know the format of the instruction, right? So you're gonna say push 6, and then we're gonna say push 5. So how do you expect this data to be inserted into the stack? So what is the top of the stack? So the top of the stack is going to be 5, because we're going to first insert 7, we subtract 4, and then we insert 6. We subtract 4, so that way we create a new space, and then we insert what? We push what? We push 5. So that's the top of the stack. If we want to pop, we copy 5, and then we increment, because now we are moving in the direction of the memory, right? And then we copy 6 and we push up. We copy 7, and then we're going to get to where the stack was. And we know when we pop, we only copy, we don't delete. That's what I said last time. So let's see if this is the fact. So if we do push, 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 let's say now say pop, right? Okay, we're going to say pop. So when you're going to say pop, let's say we're going to pop the top of the stack to EAX. And then pop the next top of the stack, which is going to be 6, right, to EBX. And then we're going to say pop the top of the stack to where? To ECX. Okay, so EAX is going to have 5, and EBX is going to have 6, and this is going to have 7. Okay, and we need to keep in mind how the stack grows, right? How the stack grows. So the stack grows in the opposite direction of the memory, right? So if the memory grows in this way, then the stack should grow in the other way, right? Regardless of how you draw it, you already know the theory, right? So let's now look at the practice. So let's create a breakpoint, and let me see if I can move this guy a little bit somewhere. Okay, hopefully here is gonna help. and then let me run the program. Okay, so if we don't have errors, we should run the program and we should see the memory. So I know this maybe look a little bit small, but I will try my best. Okay, so this is the best I can do. And then again, let me take this, something that you guys don't see, but I see from my side. Let me take this one somewhere else. Okay, so the first thing that I would like to know now, what is the stack? Okay, so I know that this is a memory A, right? So this memory A, do you see the 5 here, hopefully? Let me see if I can use the annotation. Okay, so let's say if I can go here, go to annotate. Okay, and then let's just throw. Okay. All right, so do you see this 5 right here? This is 5. So that's the memory. And we know the memory, if we have another data, is gonna go in this direction, right guys? So it's gonna go in this direction. The stack should grow in the opposite direction. If this was the stack and then we insert data, is gonna go in this direction. And keep in mind, when we go in this direction, we go by a size of what? 4, because the stack always grow by what? Grow by 4. So it's gonna insert the data and then it's gonna go backward. Okay, so the little Indian here, does the little Indian applies to the stack? Because little Indian is a concept that applies to this memory. Okay, if it's 2 bytes or more, we have to go right to left. But does right to left applies to the stack? I don't think so. We're gonna play with that concept, but let's now play with one value because we only have 1 byte, right? We're gonna make it a little bit complex a little bit later. But let me see if I can erase this part, and then I would continue on pushing the values, okay? So now I'm gonna go back here and I wanna close this annotation for now because it might affect the way we're gonna execute. And then let's now say, where is the stack? This is the main memory, but where is the stack? So that's the main memory. If you wanna find the stack, the first thing we need to do is we're gonna look at the registers. Do you see them right here? So that is the stack pointer. We should copy this value, okay, and paste this value right here in the address bar. Okay, so we go to the address bar and we paste the value that we copy from the stack pointer. So because right now we are on the .data by default, this is how Visual Studio has been set up. Okay, so what we're gonna do right now, we're just gonna take the copy of this stack pointer. That's gonna tell me where the stack is, okay? So we're gonna copy this value. Okay, we're just gonna say, do we have the copy here? Okay, let's see. Control C, and then let's go to the bar here. Hopefully we're gonna have it. So it is there, FF74, do you see it? FF74, and we press enter. So now I am in the stack. Okay, so this points at the top of the stack. So if we want to say push, we know we have to decrement by 4, and then we need to push. So that way we are not going to override the top of the stack right now. We're just going to decrement. So we create a new 4 bytes, and we push the new value, right? So let's see if we can see it. I know it's teeny tiny, but I would just now say execute push 7. Okay, so I know 7 is somewhere. Okay, let me see. Did it work? So let's now say I want to push 7, right? Okay, let me get back in here. Something is not working. I don't know why, but let me see. Okay, for some reason the program freezes. I don't know why, but let me make sure that the annotation is not there. And I don't know. Let me see what I can do. Let me try it for one more time. Okay, it seems for some reason it's not working. I will kill the process. Okay, and then let me try again, okay? So let me go and run the program again. Let me see now if we want to push. So that is the register, the register we have, which is 19FF74, 19FF74A. So I want to make sure that I'm not copying something else. So let me just say Control C and making sure, guys, okay? And Control V. Okay, so I know that's the address. And then now I'm moving to the stack. Let me see if I can run this program. So again, it's not working for some reason. But if that was to be working, let me try another thing in here. Okay, that's good. So we pushed 7 already. Okay, so 7 is somewhere in the top of the stack. Should we look for it? I have a lot of screen in my side right here. But let me push, let me look, let me do this for 6. Maybe 6 is going to be in red. So now, let's look for the 6 right here. Do you see it? It's in red. Do you see the 6 right here? And here you have the 7, right? Right, guys? So this seems to be 7, and then 1 byte, 2 byte, 3 byte, 4 byte. And then we have what? 6, right? Then 6, 1 byte, 2 byte, 3 byte. So these are 4 bytes, right? So then if we have another value, which is 5, it should go right here, right? So let's have the 5 right there. And then there you go. You see the 5 right here, right? So this is 5, 0, 0, 0, 0, 0, 0. Okay? So just it puts the value based on the order, the given order, left to right. It doesn't care about the little endian, it seems. But I will show you that case. So now that is the top of the stack. But you notice, right, the stack is growing in the opposite direction. Because we know the memory, that's the address we have right here. You see it? And the memory grows in this way, the data memory, right? Every time we insert, it grows in this way. But right here, you can see it. We have 7, and then we have 6, and then we have 5. So it grows in this way. Okay, and you should notice that it first inserts 7 and then 0, 0, 0, 0, 0, 0. Okay, so it goes in the opposite direction of the memory. So that is the top of the stack. So now we want to pop. Okay, so if we want to pop 5, we're going to expect 5 to go to EAX, right, guys? I don't know if you can see it now. I think you can. Okay, so if you want to go there, we're going to go and see 5 right here. So when we do this, we copy 5, okay, which is here, right? So this is 5. 5, it's not only this because that is the whole register, right? That's the whole space in the stack, 4 bytes. We're going to copy this to EAX, correct? And then we're going to increment because they are moving in this direction and go and point at what? 6. And if you look at the second instruction right here, which is pop, it's going to pop the value again, 0, 6, 0, 0, 0, 0, 0, 0, and push them where? And store them where? In EPX. And then after it copies, it's going to what? It's going to increment. So because it goes to the direction of the memory, it goes in this direction, not in that direction. Okay? So if that is the case, this is what we are expecting to see. All right? So let me a little bit see what I can do. So that way you guys gonna see it. Let me just minimize the memory a little bit. Okay. Okay, and then let me get this one down a little bit. Okay, I don't wanna cause any problem. I'm not ready for this. Okay, so we're gonna do this pop right now. So we should see 5, right? Then that is 5 in EAX. Do you see it in red right here? So we have the 5. And after we copy the 5, the stack pointer should be incremented. So it should point at 6. But as I said in the last class, is 5 going to be deleted from the stack? No, it's not the job of the stack to delete. It's just going to overwrite. If we push another value, it's going to overwrite it. But all it's going to do now, the stack pointer, do you see it here? The stack pointer now moves what? 4. Okay, or it moves forward 4, right? So if you notice the stack pointer right here is C, right? We are at 6. If we pop this value and we copy it to EBX, what we should see, we should increment this by 4, right? Since this is C, right, guys? C means what? A, B, C, 10, 11, 12. If we add 4 to it, it's going to be 16, right? Do we have 16 in hexadecimal? No. So it's going to be 0, right? It's going to be a 0 if we're going to go to the 16, or it's going to be 1. Remember how we do that? So we're going to be on the C side, and then we're going to say after C, it's going to be what? D, E, and then what? F, and then what? 0, 1, right? So we're going to have 1 right here, and I carry 1, so we should have 71 right here. If we add 4 to this number, play with this with your hexadecimal, okay? With your you apply your hexadecimal knowledge. All right, so let's now say the pop again. So if we pop, oh, it's 70. Why it's not 71? But it adds 4 anyway. But why it's 70? Isn't me making a mistake because you have C, and then you're gonna count what? You're gonna count 4, right? So if you have C, D, E, F, right? So you're gonna say D, E, F, 0. So I made a mistake. So if you are at C and you remember the modular arithmetic, so you go from C to D to E to F to 0. It's 4 bytes, right? So it's gonna be what? It's gonna be a 0 and a carry 1. So it was a 6, then it's gonna be a 7. Okay, so it's gonna be a 71. That's the modular arithmetic if you remember that. All right, so now we know that the value is exactly right here, the 6, and we moved. Now we're gonna add another 4 bytes, so this should be 74, right? So what we're gonna do, we now gonna go, do you see 6 is still there? Do you see it? So now we're gonna move, the stack pointer is pointing at the top, which is 7 right now. So we're gonna copy this 7 and we're gonna add 4. If we add 4, then we're gonna go what? 1, 2, 3, 4. That's now the top of the stack. It goes back to normal. That's the top of the stack right now. Okay, so let's look at that. So we are expecting the stack pointer right here to be 4. Okay, to be 74. All right, do you see how the stack pointer moves? Okay, so let's do that one. Then we're expecting 7 to go to ECX. So we have 7 in ECX, and now we know that it's 74 because it adds 4 bytes every time because we are popping. If we are pushing, then we are subtracting because now we are moving in the opposite direction. That is the memory address right here, guys. And every time you pop, you are moving in the right direction. But if you push, then you're subtracting from this. You're going up the opposite direction of the main memory or of the dot data memory for this particular example. So do you see the relationship between the stack pointer and the memory right here, how the stack pointer as a register points at the memory, and pop and push, how the pop and push works? Hopefully that's connect the idea or the theory that we learned last week. So this is exactly how the stack works. Always push, subtract 4 first, and then assign the value or push the value. If you are popping, copy the value first and then increment by 4. And you just saw an example right now. Okay, so we're gonna hold this Visual Studio for a while, and then we're gonna learn another interesting theory, which is how theoretically, how a method uses the stack to remember the caller, to remember where to return. Because if a caller, method 1 calls method 2, that cannot happen without the help of the stack. So method 1 has to do specific things that we're gonna learn today. Before you go, you better know, you better tell your callers where the control should go, okay? So the caller has to go and store some information in the stack. And the callee or the called method, if you are calling method 2 from method 1, so method 2 is the callee or the called. So you're gonna go to the called function, and the called function at the end is gonna have what? Is gonna have what? Is gonna have a returning statement. Return statement, it is an instruction, okay? It's exactly a program that's gonna go to the stack, pop the top of the stack, believing that is the return address, and that's how the control goes back to the caller, right? It's a little bit hard to explain it in the Visual Studio right away, but let me just try to go and play with the theory. All right, so let me now go back to to Visual Studio, and let me see what I can do. Okay, so we're gonna go right here, and you go back here, please. Okay, and then I wanna go back to the slides. Okay, and this is back to normal now. Okay, so in this part right here, we're gonna focus mainly on focus mainly on the theoretical part. Okay, let's look at it together. All right. Okay, so we're gonna learn today how the call and return works. Okay, it's gonna be a very intense, and it maybe takes us more time. Okay, let me see if I have the pen in here. Okay. So this is what we're gonna do. So let me first go right here. So we're gonna talk about call, return, and we're gonna look into the nested procedure calls. Once we do these two parts today, we're gonna also finish the local and global variables, and we're gonna look into procedure parameters, which is very important. Okay, so let's do that. Okay, so when you have a method, and a method needs to call another method if you are in Java. So if you have the main function in Java, okay, and in this main function, you're gonna call F1 and you're gonna pass 5 and 6, right? So this is gonna be F1 right here, and it's gonna receive A and B. They must be identified already by integer, just forgive my handwriting. And then it's gonna do whatever, and it must has a return right here. Every function must return one value, okay? So if this is the case, how this goes from here to there, because now we're doing computer organization, so we understand the hardware. So the hardware should really links this idea how the software interacts with the hardware, right? So we wanna know, but we know both the F1 and F2, they both exist where? They both exist in the dot code, right? If they are in the dot code, then that is the memory. So that is maybe the main memory, and this is maybe the F1. So you are somewhere right here in M1, and you want to jump somewhere right here, the beginning. So it's nothing but jump, okay? In assembly language and in Java, you don't even have a jump or call because that is hidden. They want to hide the details. In assembly, if you want to call this function, you have to say call, and you're going to say call F1. So this call, that's what you see right here. It is implicit here, but in assembly, it's explicit. You have to say it. If you say call or you call it by F1 in here, this is what's going to happen. The call, either implicit or explicit, it's going to do this. Okay, so it's going to offset the next instruction on the stack. Okay, it's going to push the offset. The offset means the address. If you are right here in the main function, and just imagine if there is an instruction after F1, which is read. So that is the next instruction. Before it goes there, it takes the address of this. Just imagine that the address is right here, because everything has an address in the .code memory, right? This applies for everything, but particularly right now as we are talking about the .code. If we're gonna go there, we understand that there must be an instruction in here. At least if there is no read, there should be an exit. That's how you're gonna kill the main. So that's an instruction. So before you go, take the address of this and you push it into the stack. So now we're gonna have another memory. That is a different memory, right? So that's the stack memory. Okay, so that's gonna be maybe the stack pointer pointing at the top. The call is gonna decrement it by 4. And we assume that it grows in this way. As forgive my my drawing right here, because it usually grows in the opposite direction. So if that is the growth, then it's going to subtract 4, and then it's going to have what we call the return address. The return address to what? To the next instruction. Okay, so that's what it means. I will show you that in more details. All right, and then it's going to copy the address of the called. That is the callee, or the method that we are calling. That's the F. Okay, it's gonna copy the address of the callee procedure to where? to the instruction pointer, because we know the instruction pointer always controls the dot code. Stack pointer controls what? The dot stack memory. So every segment has its own stack pointer, right? Or it has its own instruction pointer. So it has its own register that controls where you at, or it's gonna tell you where you're at in that memory. Okay, guys? So if we wanna jump from here to there, all we need to do is just change the value of the instruction pointer. Who is gonna do it? The call instruction. So the call instruction is gonna go after it decrement this and it pushes the address of the next instruction. So now it's saved. It says, I know where to return. That is the top of the stack now. Now it's gonna change the instruction pointer value. So the instruction pointer now is gonna move where? It's gonna move to the F1 memory right here. Okay, and it's gonna keep, every time we fetch, decode, execute, remember, it's gonna fetch, decode, execute, and go to the next instruction, and go to the next instruction until we hit what? We hit return. Okay, so that's what we're gonna cover next. But you need to know that the call does two things, okay? It pushes the address of the next instruction, which is we call the return address, okay? And it is gonna do what? It's gonna copy the address. In other words, it's gonna handle the instruction pointer. Okay, it's gonna change the instruction pointer from here, that points at something, it's gonna go to where? It's gonna go to the called or the callee function. Okay, kind of clear? Okay. The return, once you hit the return, so the stack pointer now is in the F1, this is our F1, so this is the F1. Just assume now we hit return. So the return also is a program, is an instruction. It does something different a little bit. So what it does right here is gonna pop, that is the top of the stack. It's gonna pop the top of the stack where? To the instruction pointer. So if we have the instruction pointer right here, we're gonna have the return address. So if we have the return address to the instruction pointer, automatically now the instruction pointer is gonna go to here. So that's how a method remember how to return the call to the caller, okay, using the stack. So the caller uses the call to push and update the instruction pointer, and then the callee is gonna use the return to pop the top of the stack. So it's gonna copy this to the instruction pointer, and after it copies that, it's gonna add 4, right? So now it's gonna return to where it was. So this is no longer a concern for us anymore, okay? The value is gonna remain there. We saw that when we pushed 7, 6, and 5. Kind of correct, kind of clear, guys? Okay, so I will show you some like more details. So if this happens to be a program that we have, so we know like every instruction has an address. So this instruction call has an address and move has an address, okay? If call needs to go to my sub, which is a procedure, right? If we wanna go to the my sub, that is my main. So I'm moving from the main to here, to the my sub. If we wanna do this, we know what the call is gonna do. So this is the offset of the instruction immediately. So this is the one, the next instruction. That is what I like to call the return address. The address of the next instruction, or you're gonna call it the return address. So the call is gonna push this into the stack. And what else is it gonna do? It's gonna update the instruction pointer from pointing at here to pointing at the first instruction here, the entry point. So now the instruction pointer point right here. It's gonna go here, it's gonna go here, and then we're gonna hit what? Return. So when we hit return, so we know that the return is gonna do what? That's the offset that we have right here, right, guys? That's the address that we're gonna push to the, the address that we're gonna push to the instruction pointer. The instruction pointer is gonna come here. When we hit return, return believes that the top of the stack, that's where the stack pointer is pointing, it has the return address. So return is gonna pop this to the instruction pointer again, because the instruction pointer controls everything. If the instruction pointer has the return address, then we are back to this instruction and the program is gonna continue from there, okay? So let me show you this with a visually. So this is what call is gonna do. So it's gonna take the address of the next instruction, which is the return address, push it into the stack. And that is number one. And number two, it's going to change the instruction pointer value with what? With the address of the first instruction in the callee or the call function. That's what the call actually does. If that is the case, then now we know the instruction pointer already now pointing right here. So it's going to be fetch, decode, execute, fetch, decode, execute, fetch, decode, execute until we hit what? Return. When we hit return, return is an instruction. When you fetch it, decode it, it says, hey, pop the top of the stack. So that's what return is going to do. Okay, so return is going to pop the top of the stack, right? So that's the top of the stack, number one. Pop the top of the stack where? To the instruction pointer. So the instruction pointer now is going to move right here. Okay, so that's what happened. When the return pop, the instruction pointer automatically goes here and is going to continue from there. So this is exactly how the stack is used to build the relationship between a caller and a callee, or it's gonna help a function remembers how to return a control to the caller, okay? Or the caller knows, oh, what if I want my control to go back? So we need a memory, right? So this is exactly what the whole idea of call return. So now we know the first concept. We can use the stack to store value like 5, 6, 7. We can also see that how a function, a program, a procedure uses the stack to store the values, okay, of the caller and the callee. All right. So now let's see if we have maybe a very interesting or complex call callee relationship. What if function 1 calls function 2, function 2 calls function 3, function 3 calls function 4, and so on and so forth. So every time we call, we know it's going to be what? Decrement the stack, push the return address, and update the instruction pointer. So now you are in the callee or the call function. If there is another call from a function 1 to function 2, that's a call. We know it. Push, decrement, sorry, push the return address, update the instruction pointer with the first instruction address and the callee part, and then the program is going to move there. All right. So if we want to do this, this is what we're going to do. We're going to look at this nested relationship. Let me see if I can move this guy here. Okay, if we look at this nested relationship, we have a call right here, right? So this call is going to do two things, right, guys? You remember that, right? It's going to push, okay? And it is going to update the instruction pointer, right, guys? Excuse my handwriting. Okay, so we know that. So we know that's going to go to the stack pointer, is going to decrement it, and is going to say store the return address. What is the return address? It's going to be the address that's going to be pointing. That's the next instruction, the address of the next instruction, which is exit right here. That's the return address. Push it into the stack. What's next? That's number one. What's number two? Number two, do what? Go to the instruction pointer and assign the address, the first address, right, in the callee. Okay, so that's the callee. That's the first address here is going to be assigned to the instruction pointer. So the instruction pointer now moves here. That's what you see. It's going to execute this, and then now it's going to again call. If we see call, then we're going to repeat this one again. Okay, let's just have it the star. So we're going to repeat the same thing here. So it's going to decrement the stack pointer from here. Okay, and now we're going to have return address maybe 2, right? And we're going to update the instruction pointer. So the instruction pointer, instead of pointing here, so that's the address that we need to store. Instead of pointing here, now it's going to go right here. So that's when we said we update the instruction pointer, because the call is going to take the address of this instruction and assign it to the instruction pointer. The instruction pointer is going to go right here. So again, right here, we're going to have another caller and callee. So it's going to decrement by 4. We're going to get the return address number 3, right? And then we're going to update the instruction pointer, right? With the first address in the callee part. Okay, so this is the first address. We updated it, then it's going to go right here. Execute, execute, execute. Now we have what? Return. Oh, interesting. Where is the top of the stack now? That is the top of the stack. It points at the return number 3. It's going to pop this and assign it to what? Instruction pointer. So the instruction pointer is going to return to what? return to 3. So it's going to come here. Sorry, it's going to come here. Now we have another return. It's going to pop the next, because when we pop, we have to increment by 4. So this is automatically go here, because that's how pop works, right? It's going to take, copy the value, and then increment. So now when we go to the second return, it's going to take the value. So the instruction pointer now is going to return address to 2, and it's going to increment it. All right. So this is how the caller and the callee works together. So if you want to see the whole relationship, that's what it is right here. Okay. So this is exactly what I explained right there. Okay. So this happens when we are right here. When we push, 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 that's going to be the stack. That's the top of the stack. Okay, so if we are in the main right here, right, guys? So that is the return address to the main. We're going to push it into the stack, and then we're going to go to the sub 1. When we are at sub 1 and we want to go to sub 2, we're going to get the address of the next instruction, which is return right here, the address, and we push it right here. So now we're at 2. If we are at 2, we need to call. That's the call. So we have to push the address that returns me to 2, and then we're going to go here. Why we don't have an address for sub 3? Because sub 3 doesn't have a call. So now that is the top of the stack. If we hit return, then we're going to copy this value to the instruction pointer, right? And then we're going to decrement this. So that's what you see right here. Okay? So when you go right here, you're going to see the return, right? So the return right here, this is the top of the stack, right? So it's going to pop that and take this one right here, pop that to the instruction pointer, this value to the instruction pointer, and then it's going to point right here. So we're going to go to where? We're going to go to the sub 1. Sub 1 is going to hit what? Return. So when we're going to this return, we again going to go to the instruction pointer. Okay, it's going to have this address. I'm sorry, the instruction pointer. And it's going to do what? It's going to return to the main, right? When it's returned to the main, this should go to the somewhere that we don't know. It should point somewhere else because the instruction pointer has to go there. You see, guys? So this is the caller-callee relationship. But this is how the stack is used to by functions, so they will remember where to return. Every time you go, you have to push your value, okay? And every time you come back, you have to pop the value, right? So this is one pop first, this one, this is the first we pop, this is the second. And if you see the empty space, it's not empty, the address is gonna be there, okay? If the time allows, I will show you that as well in the Visual Studio. Okay, guys, kind of clear? Okay. If it's kind of clear, we're gonna move on, all right? These are like common things that I would like you to keep in mind. And these simple things are mainly global and local labels. You might think, okay, what do these have to do with the stack? Just want to remind you because it's a procedures. We are learning procedures, not only the stack. So if you see in this function, you say jump to L2, right? And we have an error. We will see why this is an error. But here you say jump back to L1, right? Right? You want to jump back to this label. If you are right here and you want to jump into another .code memory to a specific part, which is labeled by a specific name, like L2, this is going to be an error. Why that's an error, but this is not. We say jump to L1. This is okay. Why? Let's look at L1. It seems L1 has double colons, right? And L2 only has one colon. So if you say jump to L2 in assembly, it is not seeing any L2 right here. So it's gonna say, I don't know what do you mean by L2, because this is considered to be what? Local, and there is no such thing as L2 in here. But right here, when you say L1, the assembler already translated this to be global, so this is gonna be looked at outside of the scope of this method. So if you wanna access some part of your code globally, then you need to just have a double colon in there, okay? And then this is gonna be our procedure parameters. We learned last time how to write a procedure, right guys? So do you remember? Can we write a simple procedure right here? So what should we do first? The procedure name, right? Let's say just add 1, right? And then we're gonna say what? Proc, right? And right here, we're just gonna say whatever, move maybe to AL5, and then we just gonna say add to AL10, and then we have to do what? Every procedure must have what? Return. Now we know why, right? Right, guys? So this is gonna be a return. And then how to end this, we're just gonna say add one end procedure. So that's where you have a procedure right here. Can you call this one from somewhere? Of course. If you are in the main procedure, right there, right, guys? I'm sorry. In the main procedure, and that's the main proc, right? And from within the main proc, you're just gonna say what? Call, right? So you're just gonna say call what? Add one. So we know call and return, how call and return works. We know that before we go to the add, call is gonna push and it is gonna update the instruction pointer. So the instruction pointer is gonna have the address of the first instruction in the callee, right? And the top of the stack, if this is my stack right here, right? If this is ASP, so first is gonna decrement this and then it's gonna store the return address. So that's the top of the stack now. That's what call is gonna do. And then it's gonna what? That's number one. And number two is gonna what? Is gonna update the instruction pointer by what? Is gonna be the address of the first instruction, okay? Address of the first instruction in the callee. So the address of the first instruction is gonna assign to the instruction pointer, and then the instruction pointer is gonna jump right here. It's gonna execute this, gonna do this, and then now we're gonna hit return. We know what the return is gonna do. It's gonna go to the top of the stack, copy this to the instruction pointer. So the instruction pointer now is gonna have the return address, okay? And once it copy this, then it's gonna increment by 4. So now it's gonna return to where it was pointing at before. And then the return now is gonna go to the main, whatever the instruction that comes right here, okay? So now we wanna see, can we, what are parameters in here? Okay, so because generally speaking, when we talk about methods, right, we talk about 5 and 6, right? So these are parameters, right? How to pass parameters. And when we pass them, how that works. When you pass this, where this go, right? So you need to understand that you're a hardware guy now. At least you have the computer organization concept in your mind and you're a programmer already. So you want to know, when I pass them, where did they go? Why that is important? It's going to help you a lot in terms of debugging or in terms of efficiency or security of your code, okay? So let's look at the parameters. So why we need parameters in general? That is the whole idea of the procedures or the methods or functions, right, guys? If it was not because of the idea of parameters, then we could have just used goto, right? But the goto does not pass different parameters, just gonna go to the same code and repeat the same thing with the same parameters. So that's the whole idea of the parameters. So we need to refer to a specific variable names with different values. That's the whole idea of the parameters. So I know you are already motivated with that. So let's look at what I mean by parameters. Let's look at passing parameters here, if you see it, using what? Using registers, okay? So let's say if we have this data or this program that has this data, this is an array, and this array is a D-word array. So we have 1, 2, 3, 4, 5 elements in the array. And then we have the sum of this, which is a space, but we assign nothing to it, right, guys? And then here we move the offset of the array. That's the address that points at this value. We moved it to ESI. And the length of this array, which is 1, 2, 3, 4, 5, is going to be assigned to what? ECX. And now we are calling. Remember when we say call, it's two things always, right? Push and update. I would call it PU, push and update. So if that is the case, then we need to go to the array sum, right? So we have to have a procedure, correct? Okay, so that is my procedure. Remember, this is just a documentation for the procedure. You don't need to have it, but it's really good to have. It's gonna teach you, at least gonna help you understand what that function does. Okay, guys? All right, so in this procedure, it's just gonna push what? ESI and ECX. Why? Because the address that points right here, if you keep reading this array, at the end is gonna change and it's gonna be right there. and you wanted it to be the way it was before you called this function, right, guys? So that's why the callee saves as the ESI. So the address right here is being pushed to the stack. So when we say push, always what, remember? Decrement by 4. And then now you're gonna push the ESI. And we also push what? The ECX, because if you keep incrementing, the ECX is gonna change by the time you return to the caller. So it's important to save those parameters, right? All right. So now we are not discussing the idea of caller and the call and return. We're talking about passing parameters. So how did we pass those parameters? We passed them using the registers, because the registers are general purpose registers. This is something new for you, because in high-level languages, you pass things using what? You pass things using the memory all the time, but here you can use the registers. It's faster and it's simple. So I will assign the first element of this array in this program, and the length, I just assign them in here and then save them in here. I don't have to save them, but this is a good practice to save. So that's what the save is. And then now you are moving 0 to EAX because you want to do the submission, right? So you have your label, you know how loop works. So that's ESI. So the ESI means the 10,000 is being assigned to EAX, is being added to EAX. So EAX now plus 0 is going to have 10,000. And then you're going to add to the address the type of the D word, which is 4, right? So now you're moving right here, right? And then you're doing the loop. So the loop is going to go to the ECX. It's going to subtract 1 from ECX and compare that with the 0, right? If it's not equal to the 0, then it's going to jump back. We're going to add this, then we're going to add this, then we're going to add this, then we're going to add that, right? So once we out of this loop, what we did in here, we pop ECX because that's the second value we push is going to be the top of the stack. Why are we doing this? We're storing because we want to know that whatever the values that we pass to this procedure, it's being processed right here. We want those parameters to go back to their original value. So that's why we need to pop them. But you need to remember to pop the last thing you inserted. Okay? And then we're going to hit the return. So this way we pass values using those two registers. Okay? So this program knows nothing about array. All it knows that the address, ESI. So through this ESI, now it knows that this is the address. Now I can access a memory which is somewhere else. That's the beauty of passing parameters, right? You don't have to have that memory or that space created in that procedure, okay? Or under the control of that procedure or that function. All right, guys? Okay, so this is another example. You can look at this example right here. So this is another way of passing parameters using registers. So you just assign values to those 3 registers right here. Assign them value, and then you call sum of. When you go to the sum of, did you really push any value in here? You don't need to save or restore any value. You just do the addition right away. So when you say add is going to assume the default value has already been assigned to EBX and EAX. You already did that in the caller side, right? And you just called, so that's the way you pass the parameters. Okay, so this is a very interesting part to pass parameters, but when you pass parameters, there is a common mistake that beginners usually do, especially in assembly, which is there are times that you should not really push, right? So let's look at this example right here. So just imagine if you are receiving an EAX value, right? And then you pushed it. Let's say in the caller, EAX has a value 5, okay? What you did in the callee, you pushed that into the stack. So now the stack pointer has a 5 right here. And then now you added EBX. Just imagine you have 2 in EBX, okay? So you're gonna add 2 to 5, then this is no longer 5, it's gonna be what? A 7, right? And then you added ECX to EAX. Just imagine if this is 3, then this is gonna be what? 10, right? Because that's a general purpose register, it's gonna be affected anyway. So now you said what? Pop EAX, okay? So when you say pop, what are you gonna do? So your result right here should be 10, right? That's what you should report. That's what you should send back, right? But what you did right here, you said what? You said pop. When you say pop, you're gonna change the value right here into back into what? 5. So that is a very difficult bug to detect. It's very hard. Okay, and the whole thing happens because you pushed when you shouldn't, right? If you didn't have this instruction in the first place, then you're going to return 10 and right away. So if you want that to be the case, then try not to push. Okay, so this is just a clarification. This is a very interesting concept, straightforward, shouldn't take us time. But this is the whole idea of linking to an external libraries or procedures, because that's what functions are all about. Can I put group of functions? We call them package. Okay, so can I have a package right here? And I have function 1, function 2, function 3, and then I can import, right, these functions into my program. That is your program right here. Can we do that? Okay. So we're going to look at that in assembly language. So we have a library that we call Arvine. And this Arvine, it's an external library that has a lot of functionality in there that we need to use. Okay, so we need to know how to import it. You know how to do that in Java, right? That's straightforward. Okay, so the whole idea of how the linker works or how the import works, it's already explained in this diagram. So this is your program, and you need to import this library, right? So you need to link this library with the operating system kernel, okay? If you link it with the operating system kernel, then now you are ready to do what? To go and execute it. Why you need to link it with the kernel? Because you create a library, and inside the library, maybe you have an open function, right? You open a file. And open is a system call. It's part of the operating system. So your library must be linked to the kernel first, because this open is provided by the kernel. And once you do it, then you're just going to execute. And then once you execute, you need the DLL. You don't need the library anymore. Now you know that the open is there. You get it ready. You attach it to the library, and now you're going to use the kernel to execute it. So the bottom line right here, if you want to invoke a method, basically what you need to do is the following, right? So you just need to say include. Okay, and you're going to say include arvine 32. All right, if you have this arvine 32, then now you can use a procedure or a function called what? Write EAX. You can use another procedure, which is clearing the screen. Okay, so these two procedures or functions, they are part of this library. When you use the include is going to do the whole thing right here. Okay, especially the one in the, especially these two ones in here. Okay, so that's the whole idea, guys. Okay, let's see and look at how that works. Let's look at the those library, because they're going to help us a lot. So these are different procedures that we have right here. So these are all procedures that you can use. Okay, these are just like some examples, like read right here. It's going to read a character, or read a hexadecimal, read a decimal, read an integer. Okay, read a string. You're going to dump the registers if you want to display the entire values in all registers. If you want to dump the data or display the data inside your memory block, you can use those. This is going to clear the screen for you. This is going to write the end of the line for you. Okay, so these are like multiple procedures you can use in your program, and this is what we call what, guys? I/O. Remember, we haven't covered I/O, so these are the input procedures right here, the I. Okay, so this is also these parts related to the output, which is like dumping or printing or cleaning the screen. Okay, guys, kind of clear? All right. So here is the other part of the I/O. Okay, this is the I/O. So that's the output. So these are, they're going to print a single character, which is a byte, or a decimal, which is unsigned. Keep that in mind, or a hex, unsigned, or write a hex byte word based on whatever you want to print out. Okay, and you can say write int, that's sign. Keep that in mind. This is always confusing my students. Okay, this one and this one. This is when you see decimal, that means unsigned. If you see it int, that means signed integer, 32-bit. And this is going to write a string. Okay, you can look at more details in the book, but I'm just going to focus into how to use them in your program right now. So if you want to invoke a procedure, you need to use call function, right? That's what we learned. And you need to have the argument that you need to pass, and you need to use the include. Okay? So you can do like, let's say in the following example, you say include, you call this library. There is a common like error that's gonna really frustrate you. I will show you how to avoid that error, because if you say include, you should remove few things from there, okay? Because there is kind of a problem. I will explain that in a minute. Let me just now focus on the command. So here we assign a value to EAX. Why EAX? Can we assign it to EBX? No. Why? Because this right hexadecimal expect the input to be assigned to EAX. So remember when we use the mul and the imul, the mul assumes the multiplicand to be assigned to a specific register. This exactly applies here. So you're gonna call this. If you call this, then you know you have to have push, and you have to have what? Update the instruction pointer. So you're gonna go to a different space in the memory. And then you're gonna run this program, and then you're gonna return. And when you return, you're gonna call another procedure that's gonna get you into a new line on the screen. Okay, the end of the line. Okay? So let's look at more examples right here. Before we go there, let me explain this. You know that if you are a matured programmer, this is something that you should not do in Java. Okay, you're gonna say IO. When you say all, you are loading the memory with 10 or 1,000, 100 functions, and you only need to use one. So if you want to import, just import what you want to use. That's not efficient if you want to import everything. Okay? So keep that in mind. We can do the same thing right here in assembly. We can just say write X what? Proto. So you don't need to use include. So you don't need to use include. Okay? So that is something that you don't need to use. You just say the function I want and say proto. And next you just need to call the function, that's all. Similar to what we did right here, but we did not use what? Call. Because right here we are uploading the entire functions, but all we need is just one function. So this is just efficiency. Okay? There are multiple examples for different functions right here or different procedures. So let me start with this very basic example, okay? So clear the screen first right here, right? And delay the program for 500 milliseconds and then dump the register values. Okay, so this is what we're gonna do. So we clear the screen and we say move 500 to EAX, and we're calling a procedure delay. Okay, why are we doing this? Because we wanna avoid the collision, because maybe the registers are updated by values and then you want to access and print their content. This could happen at the same time. If that happens, your program might crash. So to avoid that, we give 500 milliseconds. Sometimes if you remove it, it's not gonna happen, but this things happens like not very likely, but to avoid this problem, we just provide this line of code. And then we're gonna say what? Call dump. So dump is going to print out the content of all general purpose register. You can see them in here, including the flag register and the main values of the main arithmetic flags. Okay. So you can write this function by yourself if you want to do. And I think if I were you, I will make this a challenge. Why not making my own library? Just go to the book. They will show you how to do that. But it's not the focus of this class. All right, what if I want to print this string right here? We want to print this string. We know this is a byte, and we know the access for this byte, which is what? A, right? So if we can access A, then we're going to keep incrementing until we get to the null terminator, right? So it's going to be A, S, S, E, and then it's going to go like this until we get to the 0, right? That's the end. So this is how writing string is going to work. So writing string is going to expect the address of A to be assigned to EDX. And if that's been assigned to EDX, then it's going to take this address, which is pointing at A, and print A out. And then automatically it's going to move to S, S, E, M, and so on until it gets to the end. All right, so you just give it the first address and it knows what it do. It's a function, right? Pass the parameter, which is EDX. And then taking that parameter is a black box. We don't care what it does, but we know how it works. It's going to print out a string. Okay? This is like another function in here, which is you're going to have a memory, and this memory has a constant value 35, and then you want to print this in terms of binary or decimal or hexadecimal. Okay, so you want to do that, then you can simply just say print binary. So this is 35. So 35 is going to be what? That is going to be 1 byte, right? And this is 2 byte, right, guys? 3 byte, 4 bytes. So this is 4 bytes. This is 32-bit register, right? Or 32-bit memory. And this is clearly 35, right, guys? This is 1, 2, 4, 8, 16, and this is 32, right? So 32 plus 2, 34 plus 1, 35. So that's exactly 35. Okay, guys? So that's a 35. If you want to just print it as a decimal, remember, decimal means what? Signed or unsigned? I know you know it. It's unsigned. If you find it right, int, that's signed. Okay, so just going to print it as a signed number. And this is going to be 35 because it's just a decimal number. Didn't change anything. Here we want to print this one as 35 as a what? As a hex. So 35 as a hex, it should be what? 23, right? Because if you look at this number right here, what is this? This is 1, 2. So this is the 3, right? What is this? This is 2, right? So this is 23. That's why we have the 23 right here. Okay, guys? So these are more examples. This is a very important example. I like this example. This is when we read. So if you want to create a space in the memory, you can call it a file name, and you assign it 80 bytes, a space of 80 bytes, and you initialize it with 0. So what you're going to do here, you're going to move the offset of the file name to the EDX. So if you have 80 bytes, they're going to be created in this way, right, guys? And then you're going to have the file name points at the first byte. So it's going to go until byte number 80, right? Or 80th byte. Okay, so we're just going to get the address right here. We assign it to EDX. And we move the size -1. Why the size -1? Because the last one should be what? The null terminator, remember? That's the \0. Okay, that should be here. So -1, we get the size of this, which is 79 bytes, right, guys? We assign it to where? To ECX. And then we are calling what? Read string. So read string takes how many arguments? 2. Takes EDX, I'm sorry, and it takes ECX. What is it that's going to do? You insert the value. You just say, hello, my name is Awad. It's just going to read this and store it in this memory. That's it. Okay? So this is a whole program that shows you how to invoke functions. And here, and you can see in the top right here, let me see if I can move this guy a little bit somewhere else. So you see the include function right here. So, and you can try this as well, please. Take them off and comment this one out and try those proto because you only need 2 functions. You can do either way. And sometimes when you keep those here, it might cause some problems, okay? Some few things that we have right here, okay? So do you see that you have the stack already mentioned in here? And you have the model that you already have in there, right? So these 2 things here, okay, they might be already included because this included will include those already inside this library. So if you run this program and you find there's a collision, then try to take these 2 at least off. Okay, try to take this model and the stack off and see what happens. Okay? But it should work in this way right now because what is missing from here? Is there something missing from here? I want you to look at the main program and see whether there is something missing. When we declare a program, what is it that we need? The type of the memory should be flat, right? And the type of the calling convention is std call. And we need to use a stack, right? Did we miss anything else? Is there something missing right here compared to when we have like normal program? No, but as I say, these might cause some problems. In the lab exercise, you will see that note in more details, okay? But this is exactly what we are doing. We are creating a procedure. This is the name of the procedure. This is how we end the procedure. This is the return, right? And this is the way we call it. So we call add 3. We need to add 3 number. We need to pass parameters. This is the way we pass them. We pass them using what? Using registers. We give them in here, we call, so we know when we call, we should really draw the stack and try to practice. You say, this is my ESP, it points here, and this is my instruction, my instruction pointer, and it has the address of the next instruction right now, which is whatever, it's gonna be this one, the address of the next instruction. Address of the next instruction is this part. But when you say call, it's not gonna have this address. So first call is gonna do what? It's gonna decrement this right here. And then that way it's gonna push the address of the next instruction. So this is the address of the next instruction, or we call it the return address. It's gonna push it right here. And then number two is gonna update this one by what? By the address of the first instruction in the callee. So the address of move is gonna be assigned to the instruction pointer. So the instruction pointer now points here instead of here. So the control goes here, fetch decode, execute, fetch decode, execute, fetch decode, execute, fetch decode, execute, and then we're gonna hit what? Return. So return is gonna do what? It's gonna pop the top of the stack. So it's gonna look at the top of the stack and it's gonna assign this value here. Okay, so now this is gonna be the return address. So the control now is gonna go back to where? That is the instruction pointer. It's gonna go back to normal, and then it's gonna go back to here, to the call right lane. Okay, and then after we do the 0, we add, we return. Then now we just wanna print what? Integer. When I say integer, is that sign or unsigned? Because it's not decimal, right? So it's gonna be the sign. It's gonna print it out, and then it's gonna call the, to get the prompt back to the beginning of the screen, okay? And then you're just gonna exit the process. Is that kind of clear, guys? You wanna play with this example in the lab. So in the following class, we're gonna go in more advanced procedures, and then I will try to use Visual Studio to show you very interesting concepts in terms of call and return. We will see how the instruction pointer changes. We will see how the stack pointer changes and moves. And then we're gonna play with a lot of ideas, and I will show you a basic idea of a virus, how to create a simple input that's really gonna crash a program. All right. Hopefully you guys enjoyed the lecture. I know it's a very long lecture, but I have to put it all together. And we want to move on to chapter 8, and we still have the real numbers. And I hope you guys look at those slides and come during the office hours if you have any questions. Okay. So for now, I would just end it right here, and just please let me know if you have any questions during the office hours. All right, bye for now.